AI prompt caching, how senior engineers cut LLM costs and latency in production. Welcome to Agentic AI World. I'm your host, and this is episode 44 of your daily AI engineering interview prep series. Today we're going deep on a topic that separates engineers who just use LLMs from engineers who build production AI systems that actually make money. Prompt caching. Let's get into it. Section 1. What is prompt caching? When you call an LLM API, you pay for every token the model processes. In most production systems, a significant portion of those tokens are identical across requests, your system prompt, your few-shot examples, your tool definitions, your RAG context chunks. Prompt caching means don't reprocess tokens you've already processed. Instead, reuse the key value cache from the transformer's attention computation. Anthropic's Claude API was the first major provider to expose this. With prompt caching enabled, you can cache up to 200,000 tokens of a prefix. Subsequent requests that share that prefix skip recomputation, saving up to 90% on input token costs and reducing latency by up to 85%. OpenAI followed with their own automatic prompt caching for context windows over 1,024 tokens. Google Gemini has similar mechanisms via context caching. Here's the core insight. The transformer architecture computes key-value pairs for every token in the context window. Prompt caching stores those KV pairs. When the same prefix appears again, you serve from cache instead of recomputing. It's the same optimization principle as a CPU L1 cache, applied to neural network attention. Section 2. When does it matter? Prompt caching has massive impact in specific patterns. Let me walk through the main ones. Pattern 1. Static system prompts. If your system prompt is 2,000 tokens and you're running 10,000 requests per day, you're paying for 20 million input tokens every day just for the system prompt. With caching, after the first request, those tokens are served from cache, potentially at 10% of the cost. Pattern 2. Document QA. You load a 50,000 token document, and users ask multiple questions about it. Without caching, every question re-ingests the full document. With caching, the document is processed once and reused. This is where you get the most dramatic savings. Pattern 3. Few-shot examples. Your prompt has 20 demonstration examples to guide the model. Those examples are static. Cache them. Pattern 4. Tool definitions. If you're using function calling with 30 tools defined, those definitions might be 3,000 tokens. Cache the tool definitions. Pay only for the dynamic user message. Section 3. Architecture patterns. Now let me give you the patterns senior engineers actually implement. Pattern. Cache-aware prompt design. The most important rule. Put cacheable content first. Anthropic's API caches from the beginning of the prompt. If your static content is buried after dynamic content, you get no cache hits. Ideal structure. 1. System prompt, static, longest. 2. Few-shot examples, static. 3. Tool definitions, static. 4. Retrieved context, semi-static per session. 5. Conversation history, dynamic. 6. Current user message, dynamic. This is the opposite of how many engineers naturally structure prompts. They put user context first. Flip it. Pattern, session-level caching. 4 multi-turn conversations. Cache the entire conversation history up to the last n turns. On each new turn, only the new message is novel. This is how Claude's extended context sessions work efficiently. The growing conversation history benefits from incremental cache reuse. Pattern, document cache warming. For document QA systems, warm the cache on document upload, not on first query. Run a dummy prompt that includes the document immediately after upload. This hides the cache miss latency from users. Pattern, cache TTL management. Anthropic's cache has a 5-minute TTL by default, extendable to 1 hour with explicit cache control. For long-running document sessions, you need to refresh the cache before it expires. Build a cache heartbeat, a lightweight probe request every 4 minutes that reestablishes the cached prefix. Section 4. Interview deep dive, cost math. Interviewers love when you can do back-of-envelope math. Here's the model. Let's say you're building a legal document assistant. Documents average 30,000 tokens. Users ask an average of 8 questions per session. Your system prompt is 1,500 tokens. without caching asterisk. Per session, open parenthesis 30,000 plus 1,500 close parenthesis times 8 is equal to 252,000 input tokens. At Claude's $3 per million tokens, $0.756 per session. With caching asterisk. First request, 31,500 tokens at full price. Requests 2 to 8. Only 500 tokens each. User message plus response instruction. Cache hit tokens. 31,500 times 7 is equal to 220,500 at 10% price. Anthropic charges 10% for cache reads. New tokens. 500 times 7 is equal to 3,500 at full price. Total, 31,500 times $3 plus 220,500 times 30 cents plus 3,500 times $3 equals $0.0945 plus $0.066 plus $0.0105 equals $0.171 per session. That's a 77% cost reduction. At 10,000 sessions per month, you go from $7,560 to $1,710. That's $70,000 per year saved on one service. That's the kind of number that makes senior engineers valuable. Section 5. Gotchas and failure modes. Gotcha 1. Cache invalidation on prompt changes. Any change to the cached prefix invalidates the cache. A/B testing prompt variants. You're paying full price on both variants. Feature flags that modify system prompts. Each variant is a separate cache. Plan your prompt versioning strategy carefully. Gotcha 2. Cold start problem. The first request after a cache miss pays full price and has higher latency. In latency-sensitive applications, you need to account for this in your SLAs. Consider cache warming strategies and traffic shaping to avoid cold starts during peak periods. Gotcha 3. Dynamic content injection. Teams often inject dynamic content like timestamps, usernames, or session IDs into their system prompts for personalization. This kills caching. Move all dynamic content to the end of the prompt or into the user message. Your system prompt must be deterministic. Gotcha 4. Multi-model strategies. Cache is provider-specific and sometimes model version-specific. If you're routing between GPT-4 and Claude based on task type, you're maintaining separate caches. Factor this into your cost model. Gotcha 5. RAG context caching. Retrieve chunks change per query, so the retrieve context can't be cached as part of a static prefix. However, you can structure your prompt so the system prompt and instructions are cached, and only the retrieve chunks are in the uncached suffix. Partial cache hits still save money. Section 6. System design question, live example. Here's a common interview question. Design a customer support AI that handles 100,000 tickets per day with a 2-second response time target. How would you use prompt caching to make this cost-effective? Strong answer structure. First, identify cacheable content. Product documentation, potentially 50,000 tokens, highly static. Support playbooks, 5,000 tokens, updated weekly. Escalation policies, 1,000 tokens. Total cacheable prefix, 56,000 tokens. Second, structure for maximum cache reuse. Put product docs and playbooks in the system prompt. Use cache control headers to set a 1-hour TTL. Implement cache warming on deployment and after each update. Third, handle the dynamic part. Only the customer message and conversation history need to be sent fresh. Average ticket, 200 tokens. With 56,000 tokens cached at 10% cost versus 200 tokens uncached, your effective cost per request drops by roughly 95% on the static portion. Fourth, address failure modes. If your documentation cache expires mid-peak hour, you get a latency spike. Solution, proactive cache refresh job that runs every 50 minutes. Alert if cache hit rate drops below 90%. That's a signal something is wrong with your prompt structure. Fifth, monitoring. Track cache hit rate. Cache miss latency versus cache hit latency. Cost per request should be roughly 10% of uncached cost on the static portion and cache refresh success rate. That answer demonstrates you understand the mechanics, can do the math, and think about operational concerns. That's senior engineer level. Section 7. Emerging patterns. A few things to watch as prompt caching matures. Cross-request shared cache. Currently, caches are per API key and per model. Future systems may allow shared caches across different users in a multi-tenant system, reducing costs further for common documents or knowledge bases. Semantic caching. Beyond exact prefix matching, semantic caching checks if a new prompt is semantically similar to a cached prompt and returns a cached response. Tools like GPT Cache implement this. Different from KV Cache, it caches the full response, not the attention computation. Hybrid strategies. Combine prompt caching for static prefix with semantic caching for similar queries, with response caching for identical queries. Each layer has different hit rates and cost trade-offs. Senior engineers design layered caching systems, not single-layer solutions. Wrapping up, let me give you your 3 key takeaways for your next interview. 1. Prompt caching is a transformer KV cache optimization. Static content first, dynamic content last. Any deviation from this structural rule costs you cache hits. 2. Know the math. 10% cost for cache reads on Anthropic, roughly 50% on OpenAI. Calculate cost savings per session for your specific workload. Interviewers respond to numbers. 3. Operational complexity. Cache TTLs, cold start handling, cache invalidation on prompt changes, monitoring hit rates. These are the concerns that separate someone who's read the docs from someone who's run this in production. That's episode 44. Tomorrow we go into AI agentic planning and React. How senior engineers design agents that reason step by step through complex tasks. I'm your host. Keep building, keep shipping. See you tomorrow.